The last time, right, I was talking about doing a transformation, right? We are talking about doing what is called a geometric transformation. And yeah, so I was saying that, as far as 2D signals are concerned, right, as far as 2D signals are concerned, okay, the most common things are, right, what you would like to do are what is called translation, right? I mean, in the sense that what you are familiar with is probably, what I would refer to as in-plane translation. This is what probably you have seen the most. Rotation, again, this is something that you would have seen as what is called in-plane. I'll tell you what I mean by in-plane. And then scaling, this is again something that you would have seen, perhaps what's called a uniform scaling. Okay, these are things that you would have actually encountered. Okay, off and on you would have seen these things. We'll actually see, okay, what these things actually mean. So it means that you have a source image. Let's say this, let's call this as S, and then you have a target, right? And the idea is that you want to be able to, so in the source, right, you have some image and you want to apply a geometric transformation such that you get a target image. You might actually wonder why you would want to do something like that. I'll explain that along the way. Okay, why somebody would want to take an image, do something on it. As a simple example, I told you might want to zoom in, right? As was one of the examples I gave you last time. There could also be other reasons why you would like to do an operation like this. But if you're thinking that you can take a source coordinate, so assume that you have a grid, right? Wherein suppose we mark these as the xy locations, whatever 0, 0, okay, and then 1, 0. Okay, if you take x to be in this direction, y to be in this direction. Okay, suppose you assume some kind of a coordinate system, and if you think that what you want to ideally do is you want to be able to start from the source, because normally your equations will look like this. Suppose it's a pure translation, your equation is going to look like xt, yt, where t is supposed to be a target. I'm writing it as small t. This will be some source coordinate xs, ys, plus some translation. Let's say it's called tx and ty. Now it's another thing as to when you can get a constant translation for all the pixels, right? It's not immediately obvious that when you move, see all this. And of course, one more thing that I want to mention is that whenever we write these things, right, these are all image coordinates. Xs, ys is the image coordinate in the source, right? And xt image coordinate for the source, and similarly, right, what you have here is xt, yt, which is again image coordinate for target, right? Now, what is this tx and ty? So this tx and ty basically represent your image motion. So that if you kind of wonder as to when will it happen that all the pixels will move by the same amount, okay, so that is something which we'll try to explain in terms of camera motion and so on later. But as of now, just assume that just as you would take a 1D signal and translate it by some amount x of t plus b, similar to that you're doing on a spatial grid now, except that your coordinates are, except that your shifts are like along x it's tx and along y it's ty. It's interesting to ask as to when this will happen. Does it always happen? No. It's not true that you can just take a camera and move around and then hope that all the scene coordinates will move by the same amount. It won't normally happen, okay, unless certain conditions are satisfied. Okay, what those conditions are, we'll see later. But for the time being, we'll simply assume that. Now, if you say that, right, you will start with an xs, ys, let's say, which is here, and the idea is that, of course, these are still the spatial coordinates. These don't represent intensities. Okay, these are just the spatial coordinates. And your idea is that you want to start from some xs, ys, let's say, let's call this as our xs, ys location, and we want to see after we apply tx and ty, right, it is going to go somewhere here, let's say, right, onto a target grid. Now, if let's say tx and ty are pure integers for some reason, again, right, that we can't assume that they will always be integers. They could be positive, they could be negative, which means you could be shifting up, down, left, right, whichever way. But these are all pure translations, and these all mean in-plane translations. Okay, so the idea is that when you land here, okay, now if you land, if you're lucky, and then for example, if these are all integer coordinates, you would of course land somewhere on this grid where you have integer locations. But suppose let's say your tx is something like 3.7 and ty is something else, let's say minus 1.5 or something, then it means that you will land in some area which is no man's land, right? You will end up in some box inside, right? You may land somewhere here depending upon whatever is your translation. Now, if you think that now the whole point is what you want to say as to now what should right, if I land there, what should I do now? Now, one of the things, right, which you could do is you can simply assign the intensity that is here to, let's say, to one of these pixels depending upon whichever is nearest. Right, you might say that I might either floor this coordinate. Floor will mean that you know the operation of floor, right? Some 5.8 will be 5, 5.1 will also be 5. Or you may seal, in which case 5.1 will become 6, or you may simply do a round off, right? So you could try using a floor or seal, but whatever it is that you use, you'll use the same all over right, for all the coordinates. You don't change it. So seal, or you can do what is called a round off, right? You can do any of these. But then the issue is that what you cannot guarantee. It is that by starting from the source and landing in the target grid, what you cannot guarantee is the fact that you will visit every target location. Visit every target location. Visit all target locations or every target location. Every target location. What does that mean? Okay, which means that in the target grid you can be left with holes. You can be left with holes. With holes in the target grid. What does that mean? Okay, holes. It simply means that, right, these are all unassigned locations. Okay, it doesn't mean that the intensity is 0 there. It simply means that some of these locations here in this target grid could go unassigned. Now, in order to understand this, right, I'll just take one simple example just to see as to, you can of course later on try it on your own. But then prior to that, right, let me just right, give you an example. Suppose you had, let us say, okay, now I haven't talked about scaling yet. All right, I mean, I'll kind of say come back to this, okay, in a minute. The other operation that you will tend to do, okay, I'll kind of say come back to what I mean by, right, what I really mean by you will be actually left with holes in the target grid. I'll come back to this once I talk about rotation and scaling. The other two operations which are in plane are as follows. So when you have xt, yt, and then if you're talking about a clockwise rotation, then it will be like, again, assuming that that the convention is this is x and that is y, okay, assuming that to be the convention, then xt, yt will be some cos of theta, sin theta, minus sin theta, cos theta, and then multiplying your xs and ys. Okay, this will be like, you take your source coordinate, apply this transformation on that, and then it takes you to a target coordinate xt, yt. The whole idea is that you want to be able to assign intensity. So ideally, whatever is the intensity here, that should get you say assigned in the say target grid. But then if it falls somewhere in this kind of what do you call, in the center or somewhere within the box, then you wonder what you need to do with that, right? So that is what will create issues. Now, this one is called actually in plane rotation, which actually means that if you had a camera like this, okay, suppose assume that this is a camera sensor plane. Okay, then it actually means that in plane rotation is something like that. So it's about suppose you assume that the camera optical axis is coming out like this, then if you were to rotate this image plane, right, now about this optical axis, then what you will get is actually what is called an in plane rotation, right? That is the angle theta. So it's more or less like a theta z. If you wish, you can be more explicit, but right now we'll just simply write it as theta. So this is really a rotation about the optical axis, and then your camera kind of rotates like that. Okay, so that is why it's called an in-plane rotation. Outer plane would be something like that, or something like this would all be outer plane. And outer plane, eventually, of course, we would like to be able to deal with all kinds of motion, right? We don't want to stick to just an in-plane translation is something like that, where you can go within the sensor plane, you can go up and you can go up down, or you can go left right. In plane sort of a rotation is this, and ideally, right, a camera will undergo what is called a 6D motion, which means it can undergo a rotation about all the three axes, and it can also translate along x, it can translate along y, it can also translate along z, right? So eventually you want to be able to have this kind of a transformation that will take you from one image to another under a general camera motion. But for the time being, just to set the tone, what I thought is we'll start with a simple case, something that you're all familiar with. Okay, so such a rotation is called in plane. Okay, and this is called an in-plane rotation. And then when you kind of go to scaling, of course you would guess what it might look like. Sometimes this can be trouble. So then what you have is scaling. Okay, scaling will typically look like A0, let's say 0B. What is called a non-uniform scaling. Again, of course, you have your xt yt on the left, and then this is the acts like an xs ys. So it's simply like a times xx is xt, and then yt is simply b times ys, right? So you're simply scaling, and this is called a non-uniform scaling because a and b, right, need not be the same. If it is uniform scaling, then, or isotropic as it is called, then a is equal to b. This is what is referred to as scaling. And these operations, right, which we are saying that we will take an image and then go to another, okay, by doing some kind of a geometric transformation. Suppose, for example, I look at scaling, right? This is something that you can associate with, with, let's say, something that you're familiar with is zoom in and zoom out. Okay, this is like zoom in and zoom out. And in all of this, right, please bear in mind that the image size is not changing. Okay, imagine that right, you have a camera which is actually capturing a picture of a scene from here, and suppose it moved here, and then, right, it took, let's say, one more image. The whole idea is that ideally, right, what we would like to eventually be able to do is why we are even talking about going from one image to another. How to do that operation is to eventually be able to relate, okay, two images taken from a camera. Okay, but then when the views are not the same. So you could have, let's say, one viewpoint from here you take, and then you take another from another viewpoint. These two images, they're exactly of the same scene, except that, right, it need not have been taken from the same, that is original viewpoint. And you want to be able to say relate the two. And there are several reasons why you would want to relate the two, which I will talk about. But right now, one of the things, right, that I thought when I talk about scaling, right, I'll actually mention is what is called zooming in and zooming out. I mean, when you buy a camera, let's say, right, when these guys advertise, they talk about what is called an optical zoom, and they talk about something called a soft zoom, right? So when they say optical zoom, what they mean is a real optical zoom. See, so there is something called the optical zoom, okay, and there is something else which is called the soft zoom. Okay, soft is like I say algorithmic zoom. By soft we mean, it's like software, right? So it's like soft zoom. So it has to do with some algorithm, some signal processing or image processing that is going on. Optical means you are actually having a lens whose focal length can be changed. Okay. Now in reality, right, when you actually zoom in, you actually expect that you would be able to see finer things. Now, how do you see an optical zoom? Right, in order to see an optical zoom, imagine that let's say, right, you have actually a pinhole camera. All that we are talking about is really, if I have not mentioned it already, this is all for what is called a pinhole camera. Okay, this is not the same as what you carry with you, which is basically a lens-based camera. Right, all of us carry what a lens-based. Why we carry a lens camera is something which we will talk about later. But right now, it's like what we are assuming is simply a pinhole model. Because the moment you bring in a lens, there are so many other things that start to happen. Okay, what you can focus, what you cannot focus, and so on. Whereas if you can take a pinhole, okay, that issue is simply not there. And pinhole is the simplest model to start with, and then kind of, right, one can start to say escalate it. Okay, so what it means is that you have, let's say, so you could have a scene, right, on the left, and then the entire scene. So you could have a scene that is mapping, okay, through this pinhole, and then imagine that. Okay, let me draw the same color. Now here is your image plane, and from here to here is your say focal length, okay, of the camera. Now what this actually means is that because your sensor plane is fixed, right, now if I approximately draw something with a green lines, then what it means is that probably, right, I can see. Okay, now let's assume that the sensor ends there, and okay, I cannot draw it too accurately, but let's assume that. So what it means is that your field of view is this. That means so much of the scene, right, you are able to see. Now suppose for some reason, okay, you actually you make the f smaller, the sense that you bring the sensor plane forward. Okay, so now the sensor size cannot change, right, the image plane, so we'll keep it at the same size. But now what we have done is we have actually reduced the f. Okay, under this circumstance, if you see, right, what all you will be able to see, you're kind of going right there. Right? I'm not drawing a straight line, but then imagine that, right, you would be going like that, and then from here, right, you would be going like that, okay, or somewhere there, okay. Oh, that's too bad. Okay, let's try drawing it a little better. Okay, yeah, so this is going to look somewhat like this. Okay, so now you see that, with a smaller f, when you change the focal length, right, what has happened is you have a field of view, right, which is now much larger, okay, which is okay, which is like which is okay, which actually means that you are able to see a larger portion of the scene, but then which also means that you will actually lose out on finer details, because if you see, right, a larger scene is now mapping onto the same sensor area. Earlier, right, you had a smaller area of the scene mapping into the same sensor area. Now you have a larger scene, right, kind of say mapping into it, correct. So when you have a small f, such lenses are called wide angle. Wide angle is like small f. On the other hand, okay, if you had the flexibility to let's say to change f, and then you would increase it, let's say, let's go here, okay, increase our f, okay, make it okay, whatever, let's say initially it was f1, and then maybe, right, this was f2, and now we go like f3. Then you can kind of clearly see that, maybe I'll draw with red. So now what will happen is, okay, you will be able to see this portion, and similarly out here, right, you might be able to see that portion, okay, of. So again, now you have field of view has now become smaller, and such a thing is called a telephoto lens, a telephoto lens, or what has a large f. Right, now this is what is an optical zoom, right, in the sense that right, you change the focal length of your lens, and then that kind of allows you to capture the way you want, right. So that is why when you sort of zoom in, right, then you're able to see things which are of a finer detail, and then when you zoom out, right, you tend to occupy a larger part of the scene. Now when you do a soft zoom, okay, you're not doing this. Okay, with respect to a soft zoom, all that, so right, this is all optical. This is what you mean by an optical zoom, where you can actually change the focal length, and then start to, right, image portions of the scene according to the way you want. Now as far as soft zoom is concerned, this is algorithmic. So what it means is that if I had somebody's face here, right, suppose I had somebody's face here, and then suppose I want to zoom in, okay, what I kind of say effectively I'm asking is, a part of this should occupy, so in a sense, right, what I'm asking is, this portion out here should go and you see occupy this whole thing, right. That's what you mean by a zoom in. So for example, here, okay, if you feel that the nose and the eyebrows are the only things that are present here within this inner circle, then right, that is what will appear here. But then yes, because you're okay. Now you see, in this case, right, when you actually increase the focal length, right, see, I mean, so see this region of the 3D scene that is getting kind of mapped onto your image plane. You're now mapping a smaller region onto the same area, right. Your sensor is not changing, whereas in the other case, your field of, I mean, you're seeing a lot more of the scene, but then your ability to see finer details is no longer there, because a larger portion of the scene is occupying the same sensor area. A large portion coming on and mapping to the same sensor area, versus a smaller scene area mapping into the same sensor area, you would naturally be able to see finer details with respect to the one that has a larger f, right, because your field of view is now going to say restricted. So the point is, right, so when you have a soft zoom, okay, so what you're saying is this inner portion, right, should actually map on to this image grid that you have. But then when you do an algorithmic thing, right, you're not really, so unlike this in an optical zoom, where let's say when somebody says that he's zooming in, he's actually picking up finer features. Whereas here, right, I mean, for the same reason, right, as this person asked. So the fact that a smaller portion of the scene is now getting mapped onto the same area, that means your ability to see finer details is higher now. Now, but here when you do a soft zoom, when these people say that I have a 100x soft zoom, it doesn't mean much actually, because right, all that right, they are actually doing is they are kind of taking the existing information and trying to kind of see fill up this grid, but there is no new information that they have in order to be able to tell, right, what are really the finer details. That is also the reason when you actually do a soft zoom, right, you tend to see images that don't look so great. Whereas when the same thing you do with an optical zoom, you have this feeling that you're able to see, which is why optical zoom is a lot more expensive. You pay for it, right, because it gives you the ability to actually see things in a finer form. Whereas when you do a soft zoom, it all depends upon what kind of an algorithm you are using in order to be able to take information that already exists, and it is simply trying to kind of use existing information in order to be able to build up an image that seems like, that seems to give you fine information, but that's actually not true, because there is no new information that has come in. Now, right, this doesn't mean that right, people haven't done anything from going from what is called the super resolution and all that. People do talk about going from one image to high resolution and all, but that is something else totally. Okay, here the way your cameras operate, the soft zoom and all, is simply this. Okay, they are not doing any kind of deep learning and all. This is a simple algorithm that just takes this image and then it tries to build this. Now again, in all of this, you are going to start from a source, and then, right, you're going to try to go to a target. Right. So what I want to now do is come back to this issue, right, which is the issue about the holes, right, which I actually mentioned. So if you think that you can start with the source and then, directly start filling up the grid in the target, right, you could have issues, and what those issues are likely to be, right, we'll see in a short while. So let us say that let us kind of go to the scaling example itself. Okay, and since we have already seen it, let us say that I have my A, which is equal to 1.2. Suppose I take some A, okay, which is equal to 1.2, which then means that if you go back to the equation, it means xt is equal to A times xs, and then yt is equal to, let's say, A times ys. Suppose we assume that we are doing uniform scaling, right, yt is equal to A times ys. Now, since A is a number right now, which is actually, right, more than 1, greater than 1, now what do you think this might be? Would this be a zoom in or zoom out? If A is actually greater than 1. Zoom in, right? It will be a zoom in, because how do you, one way to guess is that, suppose you see xs, right? Suppose you do write xs is xt by A, and therefore, right, what will happen is, right, no, prior to that, let me just do this whole business, right? I've been leaving that. Let's kind of come back to this, okay, in a minute, but this is zoom in. Okay. Now look at let's say, suppose I have these locations, okay, that I am writing xs at 100. Okay, suppose this is like the 100th column. Okay, whatever be the y coordinate, let's not worry about the y coordinate right now. 100, 101, 102, 103, let's say. Okay, suppose I want to know where these coordinates are going to go. Assume that, let's say, y is the same for all of them, just for simplicity. Okay, your ys. So it could be like 100, 50, 101, 50, 102, 50, 103, 50, something like that. Okay, but of course in this case even y will change because it has some A times ys. But let's just focus on xs. Now if you look at xt, okay, so suppose we take this relationship as it is. That means we start from a source coordinate, and then right, we try to see where the target coordinate will go. So when you take xt, right, it will be 1.2 into 100, which is actually 120, which is fine. Okay, which means that we should be able to say map it. Okay, so that means suppose 100 comma whatever is that y coordinate, the intensity there will get mapped to 120 comma whatever is that yt. Okay, correspondingly. Suppose let's say ys was 50, then yt in this case would be 50 into 1.2, 60. So it will go to 120 comma 60. Right, that is where the intensity will go. These are not intensities. Right, these are the coordinates. Now when you take 101, right, now I have the value here. 101 goes to 121.2. Okay. Those I have it here. So 121.2. So suppose we do a rounding, let's say, right? Because 121.2. So what you would typically do is what is called really a nearest neighbor, or in a sense you may just do a kind of a rounding off. So what you will do is in your target grid, right? If you right, you're somewhere here, and 121.2, right, could be, let's say, right, somewhere here, and then what you could do, you can do any of them. You can do round, you can do seal, or right, you can do floor. But suppose let's say we do some rounding. Suppose we decide that we'll do rounding. Then what it will mean is you will actually map it to 121, right? 121 will get that intensity because you're just doing a simple rounding off. Okay, so 121, so 120 has gotten filled up. 121 has also gotten filled up because we did this rounding. 102, if you look at it, that will go to 122.4. Now again, right, 122 to 122.4 is again in no man's land. So what we could do is we could round that, and we will say that, so 120, so there is no issue here, 121, then 122, okay, we are able to map. So till now I don't see any holes. Now 103, when you do, what do you find? You get something like 123.6, right? If you multiply 1.2 with 103, you'll get 123.6. Now if I do a round off, the 123.6 will go to actually 124. Right now what will happen is, so this pixel, this intensity at 103 comma whatever it is, whatever is the corresponding y, wherever it is supposed to go, so that will get mapped to say 124. Now what do you see between 122 and 124? There was a whole row which was actually 123, right, which you did not land at all. After this, right, you will just go on, right, and then what may happen is, not just a small example, just to illustrate the fact that why, when you start from the source and then you try to land on the target, there is no real guarantee that you will land on each of these locations. There is no such guarantee. If you try something else, maybe if you try seal, then somewhere else you might actually miss out. Okay, so which is why people never do source to target transformation. People always do what is called a target to source transformation. So S to T, right, is not the thing that you do, principally because of the reason that it can cause holes. Okay, this is what we mean by holes, and holes doesn't mean that those locations have zero intensity. It simply means that, right, those are all unassigned because you never landed there. So if you look at the target image, right, you will see that you've got intensities in many places, but then there are places where you have not been able to assign any value at all. Okay, which is bad, right? You don't want to take an image and, in which, let's say, some of these locations don't have any intensities at all. That means these are unassigned, right? You don't want unassigned locations. So instead, what is done is a target to source. By target to source, right, what you can do is you can definitely ensure that every location in the target is assigned an intensity. So what that means is going the inverse way. So now what you do is, instead of going this way, you go the inverse way. So Ys is equal to Yt by A. Okay, and now you will also see why this should be a zoom in. Okay, so now what it will mean is, so if you take, so suppose you take the maximum value, right, in xt, okay, well, let us say that it's a 256 cross 256 size. Okay, then when you take a maximum of 256 and divide by a, which is actually 1.2, which is a number greater than 1, then it means x's and y's will fall inside inside of 256, right, which means that that a smaller portion in S is getting mapped to a larger portion in T. Right, you see that, no? So if you're dividing by A, the target coordinate, assume that you are at the extremity of the image. Let's say you're at the end of the image. When you multiply by A, which is greater than 1, that means you will actually go back to a source which is inside that grid, right? Which means that a smaller portion of S is coming and falling, on a kind of larger. It's being splashed on a larger sort of a grid, right? That is what is happening. That's why this zoom in. If it was the other way around, if A was 0.8 or something less than 1, it would be zoom out. Okay, in a real camera, of course, when you zoom in and zoom out, right, you don't see, zoom in is easy. You don't, you see that, you can easily see that a portion here will come and sit there. But if it is a zoom out, let's say, right, then what might happen is, okay, you might, so what that means is, you might actually end up with some, especially when you write a lab assignment, right, what will happen is you won't be able to access information outside this grid, right, because you don't know what lies outside, and therefore what will really, so zoom out will mean what, that is the entire thing, right, will come and sit as a smaller region here. Now in order to fill something here, it will go outside the grid now, but then when it goes outside the grid, you don't know what those values are. So typically what we do is we just leave them as zeros in a lab assignment. In a real camera, it doesn't happen, because some new information will come and sit there. When you zoom out, you don't find zeros there, right, simply because the rest of the scene will come in. So imagine that if you had access to information outside, you can actually plant those values here. But that will mean that you'll have to look at the image as being on a larger grid, and then the image as being sitting inside it. And then when you, okay, do you see this? So for example, when you divide 256 by, let's say, 0.8, then it will be a number outside this 256 cross 256, right? Now if you knew what was outside, you could of course bring that and kind of copy it here. But then if you did not know, right, which will normally the case, then we simply ask you to put zeros here. That's only an implementation issue. Okay, that doesn't mean that in a real zoom, okay, right, that is what will happen. But zoom in is not a problem, because only a smaller region is going there, and therefore there is no reason to believe that you will have any empty regions here. Zoom out can have empty regions in your own implementation, that is all. Okay. Some people, what they do is they just assume that they will assume that they know the values outside of this grid, and then they will copy, which is okay. But then they should tell upfront, right, that they are doing something like that. Now, why does this not have a problem, right? In order to see, if I go from target to source, why that is okay. In order to see that, right? So imagine that right, when you're starting from some, right, xt yt, and then that is your target, and then okay, you have your source here. This is again your target, this is your source, and now you are starting from target, right? So here are your integer locations on the grid, right? You know those locations. You don't know what intensities to assign. So suppose you start from here, and then, right, suppose it so happens that you end up somewhere again in a kind of a no man's land here. But now the advantage, right, which you have is you could try what is called really a nearest neighbor. Nearest neighbor in the sense that you could assign, any of these 4 location intensities of these 4 locations, depending upon whichever right this guy is closest to, which means that if this happens to be closest to this pixel, then that intensity will get assigned here. If this lands such that it is closest to this pixel, then that intensity, right, will get copied here, and so on. Okay, so that way, even with the simple nearest neighbor, you will always be assured that you will land here, and then for every guy here, there is a value here that you can assign. But normally, if you do something like a simple nearest neighbor, right, this can lead to what is called jaggedness. It won't look very natural. The good thing about this is that you are, of course, completing the grid. You are not leaving anything unassigned, right? For every location, you are able to assign an intensity. But what will happen is, doing something like this will give what is called a jagged appearance. I mean, if you actually look at images like that, which I will show today, right, they will have a kind of a wavy or what is called a jagged appearance. Instead, what is done is, people do what is called interpolation. Okay, interpolation is what is actually normally done. By interpolation, what we mean is we try to make use of as much information as we have in order to be able to make a reasonable guess about what this intensity should be like. Now, there are various ways to actually interpolate, and the one that we will talk about is one of the simplest, but then that should give you an idea about how these things work. What's called a bilinear interpolation.